Part B. Derive an expression for the total DC error as a voltage referred to the input to the output. You may all be asking why I've written that down. You will see in a minute, and I will tell you how many students don't note that point. Include the effect of both bias and offset currents, and clearly state any assumptions that you make. Assumptions. We're assuming that we have linear circuits, so we can assume superposition applies. Op-amp is perfect with the addition of current and voltage sources to create imperfect model. And the third one is a classic op-amp one. Zn equals infinity.
Professor.
Yes.
Can you move this paper?
Sorry. Yeah.
Right.
Thank you for that. I'm sitting here writing frantically away, and you can't see what I'm writing.
Okay.
All my pearls of wisdom are being wasted. Okay, so we've three assumptions. We've assumed linear circuits, so we can assume superposition. Op-amp is perfect with the addition of current and voltage sources to create imperfect model. And the op-amp ones, Zn is infinity, gain equals infinity, and therefore V plus will equal V minus. In other words, virtual earth principle applies. And those are our assumptions. Please write them down. Please write them down clearly so I can read them. Most students, probably 70%, lose marks in this question because they do not write down this stuff here. Have I made myself clear, students? Okay, so please write that down. Now, if we go back to our little circuit here, and we can start doing the analysis. And first of all, I'm going to say at V plus, at the terminal V plus, so V plus equals VOS minus IBRX minus IOS over 2 times Rx. So let's have a quick look at the little circuit here. So V plus, which is this node here, and that one there is V minus. So V plus equals the offset voltage minus the current flowing through IB through Rx minus the current flowing through IOS upon 2 times Rx. So here we have IB plus IOS over 2 flowing in that direction there, and that has the effect of changing the voltage at V plus. So we now have an expression here is VOS minus IB times Rx minus IOS upon 2 times Rx. You could have written that minus IB plus IOS over 2 times Rx. Your choice. Okay. I will try not to move things too much. So we've got V plus, and now we can do at V minus, and we do exactly the same thing, but we calculate out the voltage at V minus. CV minus equals the voltage at the output times RB over RF plus RB. And I should also say, let RB equal R being in parallel with the R. In other words, these two input resistors here, I'm going to consider as a parallel combination pair. You do not need to do that, but it just makes the math slightly easier and it makes it tidier. So I've combined both these resistors here into something we call RB. So we've got V minus equals V out into RB upon RS plus R over RB minus IB into RF in parallel with R plus IOS over 2 into RF in parallel with RB. For perfect op-amp, V plus equals V minus. Therefore, V out into RB over RF plus RB equals VOS minus IB RX minus IOS upon 2 RX plus IB minus IOS upon 2 into RF in parallel with RB. And that's just taking this equation here, and moving the terms around a little bit to make them all neat and tidy. So V out equals RB plus RF over RB.
Professor, please move the version now.
Yeah, sorry. Where was I? V out equals RB plus RF, VOS plus IB times RB over RF plus RB into RF plus RB over RB minus RX over RB minus, because I don't have a big enough sheet of paper, RF by RB or RF plus RB so final result gives us V out equals RB plus RF over RB VOS plus IB into RF minus RX into RF plus RB over RB minus IOS over 2, and it'd be a bit messy here, RF plus RX into RF plus RB over RB. Okay, so a bit of a squeeze there. So that is our final term here. And the important thing that you note is that we have an IB term here, and we've got RF minus an RX, and we've got an RF plus RX here. And if you look back in your notes, you'll discover that that's the way that we express it in the notes. and it becomes clear from that what the calculation is. Now, earlier on I said I wrote down referred to output at the start, because in last year's exam, and there's usually a question of this type, I'm going to guess of the students who got it right, of the students who answered this question adequately and kind of got down to this area, about 75% of those failed to refer it to the output. So they lost marks because they did the calculation perfectly, but referred the error to the input and not to the output. So please read the question carefully. I don't want to see those exam marks thrown away again. But generally, the things that people failed in this question was they wouldn't state their assumptions and they didn't refer it to the output. When you're doing your calculations, I appreciate that it was pretty boring watching me writing all this out, but trust me, when you're doing the your calculations in the exam, please show you're working. Show it written out quite clearly like this, so I can give you marks in case you make a mistake. If you do something silly like put a minus in there instead of a plus, then your bottom equation is going to be wrong. But if I can clearly see that you've just made a silly algebraic error up here, I can still give you most of the marks. But if you just start from this point up here and then jump down to this point here and you've made a mistake, I can only give you only a few marks because I can't see where you've made your errors. So showing you're working is good. I appreciate that it's boring to watch, but it's important to see.
Professor, it's time for break.
Oh, so it is. Right. The one thing I would ask you all to do, let me just stop the share, is last week I asked you all to complete the survey on the Moodle site. Thank you very much for those of you who have done it. For those of you in the class today that did not complete the survey, then please go onto the Moodle site just now and complete the survey. It's very useful getting the feedback, and I can use it for next week, next year.